Hi, everybody. Welcome to our next round of fellows talks. We have 6 fellows presenting today. First up is Camille. Camille, whenever you're ready, go ahead and get started.
Okay. So, hi, I'm Camille Sicat, and this is my fellowship on the optimization of the Rucio-SENSE DMM with mentorship by Ishay Aurora and Diego Duvella. So before I start explaining what my fellowship is about, it's probably best to recap what the Rucio-SENSE DMM is and why I was working on it. So current experiments at CERN, such as the compact moon solenoid, generate as much as 20 petabytes of data per year, with future planned experiments, such as the High Luminosity Large Hadron Collider, generating up to 30 times more data. To replicate this volume of data across different storage sites, we need speeds of at least 100 gigabits per second, with an estimated speed of 400 gigabits per second needed between sites in the US. Then our current network model is push now, worry later, which means that networks will be dominated by large transfers, including these high volume of data produced by experiments. Therefore, we need more accountable network usage to ensure that transfers go through smoothly. And that's where the Rucio-SENSE DMM comes in. So the Rucio-SENSE Movement Manager, DMM for short, is an interface between two different pieces of software, Sense and Rucio. So Sense allows for customizable multi-domain orchestration for use on experiments with individual domain science workflows and requirements like those we have at CERN. It pushes quality of service and routing rules for data transfers. Meanwhile, Rucio is CERN's data management software and provides for scalable data storage, transfer, replication, and other services across physical locations. It also allows for the individualized tracking and tagging of data, which is useful for when DMM comes in to grab the source and destination RSE names, number of bytes, and priority of the data to be transferred, also known as a rule. Then Sense will construct peer-to-peer VLANs between the set of endpoints grabbed from Rucio. And then from there, while the transfer is going, DMM will monitor the status and performance of all data flows. And based on the transfer metadata, DMM will calculate and provision network bandwidth for each rule, constantly assessing current bandwidth usage and reallocating depending on the priority of new rules being added or rules being completed. Now, with that all of the way, it's time to talk about what my fellowship was about. So the main goal of my fellowship was to help make DMM more robust so it can work in its goal of making network usage more accountable, which means being able to track transfer rates and points of failure. To that end, I implemented the DMM monitoring daemon, which has two major functions. Online monitoring, which is a live tracking of throughput calculated every 10 seconds using metrics from Prometheus. This allows it to act as a live performance report for transfer rates, points of failure, and other metrics as large sustained changes in throughput, an indicator of something major happening. And while we still need to further test it and refine it, right now it's in a good working state. And as for offline monitoring, this function correlates data from completed transfers using metrics from Prometheus and FTS to analyze completed rules. So basically we can see expected versus actual throughput and what specific stages of transfers failed. This allows us to compare different transfers from the same or different locations, and let's see overall performance. Now then, out of the other goals in making DMM more robust was the optimization of the network bandwidth algorithm and DMM's interactions with Rucio. And while we did test implementations of weighted fair queuing, linear programming, and maximum fairness algorithms for this purpose, they did not perform as hoped. So for further optimization, we have to perform more research and more testing. And due to time constraints, we were not able to optimize DMM's interactions with Rucio during this fellowship. So while I was working on all of this, I developed strong skills in GitHub, Python, SQL, HTML, and graphing algorithms, and gained hands-on experience integrating Docker, Kubernetes, Prometheus, FTS, and Flask for project development and deployment. And in doing so, and also thanks to the great mentorship of Diego and Deshay, I was able to reaffirm to myself the importance of collaboration and time management, because without both of those things, I would not be able to accomplish any of the above. So, in summary, because future experiments will generate large amounts of data, the fellowship was focused on making the Rucio-SENSE DMM more robust, so it's capable of holding networks accountable for data transfers involving the large amount generated by these experiments. And in my fellowship, I was able to successfully input throughput monitoring, both online and offline, although of course further optimizations are possible. And with some testing done on optimizing both the network bandwidth allocation, and though again further refinement is necessary, and also some further optimization of the Rucio interactions is still needed. So yeah, thank you.
Thank you, Camille. Any questions for Camille? No. Well, I'm glad it sounds like you had a good experience, and thank you for your talk. Next up, Alexander.
Okay, so I'm Alex, and today I'll be talking about leveraging ServiceX to transform PHYSLITE data into flat N-tuples with systematics. So how can this be done? So we can encapsulate TopCP toolkit in a Docker container and then make that accessible on ServiceX. So what is ServiceX? So here's the description that I found for it online. It's an experiment-agnostic service to enable on-demand columnar data delivery tailored for nearly interactive, high-performance, array-based Pythonic analyses. It provides a uniform back-end interface to data storage services and an intuitive front-end for users to enable columnar transformations from multiple different data formats and organizational structures. So basically what that means is that there's a number of applications on ServiceX that transform data into a more user-friendly format. So some examples are the uproot transformer, which takes in a JSON file that the user wrote and then uses the Python's uproot library to transform flat root and tuples. There's a funcadl transformer, which does something similar with C++, and there's a Python transformer that basically takes in a Python script that the user wrote and then runs it on some input files. And then there's other ones. So what I'm trying to do is to put TopCP toolkit, encapsulate TopCP toolkit on ServiceX. So make another transformer out of TopCP toolkit. So let me describe TopCP toolkit. So PHYSLITE is a lightweight file format used to store particle collision event data. PHYSLITE files are designed for C++, making them difficult to use in the Python ecosystem. Systematic uncertainties are not directly stored and must be calculated from these files, but there currently exists no Python libraries to do that. However, these files can be N-tupleized for compatibility with the Python ecosystem. Using TopCP toolkit, these files can be filtered and N-tupleized according to user specifications. Additionally, TopCP toolkit can calculate systematic uncertainties from these files, information that would otherwise be inaccessible once N-tupleized. TopCP toolkit is a powerful tool, but it can be cumbersome to set up. By making a TopCP toolkit transformer for ServiceX, we can capture the full analysis power of TopCP toolkit while skipping the many steps needed to set it up and we can also access potentially more computing resources than locally available. So TopCP toolkit takes in the PHYSLITE file, runs it through some software, and then spits out your nice N-tuple with systematics. So this is what it looks like to use TopCP toolkit normally once you've set it up. So this is just the Python file that TopCP toolkit has inside of it. This is it's a list of file locations of your PHYSLITE files, which could be on the internet. This is just the name of your output file. This is where the real physics happens. So this is a folder full of YAML files. And this contains all the information about the files that you want to extract. And then here's some other options like no systematics, or I want 10 events, or stuff like that. So here's the part where the physics, quote unquote, happens. So this is those YAML files I was talking about where the analysis happens. So you can see, we specify some information about jets. We want to say there's like a minimum PT, a max ETA. We could say we want electrons, specifying this information, or muons specifying this information, etc. Okay. I also mentioned Docker, which is an important part of this process. So we want to capture TopCP toolkit in a Docker container. So I just want to explain Docker real quick. So a Docker container is like a mini computer on your computer, kind of. So this is a script that will set up that mini computer. You see that it runs some commands inside the container. It sets some environment variables. It copies some folders from your computer onto the Docker container. And then it runs some more commands, etc. So here's how this is kind of the architecture of putting TopCP toolkit into the Docker container. So the Docker container will exist on the ServiceX host, and then it will be connected to the host via these things called volumes. So it's basically directories that are linked from the host to the container. And this is where you put in your input files, your output files, and etc. And then those get put into the Docker area where TopCP toolkit exists. And then TopCP toolkit will do its thing and then spit out the files that you want. So here's kind of like, this is the workflow for the func ADL transformer. And underneath I basically wrote down like a abridged equivalent of TopCP toolkit. So you send in your query, then that goes to this other Docker image that you have to write called the codegen image, or that we had to write. Sorry, the user doesn't need to worry about this, but we have to write a codegen image, and then that takes in the query file, generates some code, and then your PHYSLITE files get looked up, and then the generated code and the PHYSLITE files get passed to the science image where TopCP toolkit is. So here's kind of like like a flow chart, right? So you start with the client, the user, they send their YAML file and the PHYSLITE URLs to the ServiceX server, and then TopCP toolkit runs the codegen, generates some code, and then that gets past the TopCP toolkit science image, which then gets which then creates the N-tuples that you were looking for. And then those will just exist on the ServiceX server, and then you can download them or download the URL. So here's kind of what the client would, oops, sorry. So this is what the client basically will interact with, is just like a Python script where they just have to import ServiceX and then send off your data set and your analysis file. Okay, so what we've done so far is we've made the science image, the cogen image. We've also made so these are a science image. I guess I should say a science container to make it clear. We made the science container, the cogen container. We've also made one for building X509 proxies, which is something that you need to access a lot of these files. Yeah, so that's handy. And then we've also made a ServiceX test harness, which has been useful in developing these images and could also be used to develop images in the future. What we still have to do, we have to make sure that the science and the cogen images are communicating properly. We need to put the finished product on ServiceX itself, and then we need to write an example client script so that the user doesn't have to write that from scratch. Any questions? Oh.
Thank you, Alexander. Yeah, one person has their hand raised. Vangelis?
Hi, thanks for this work. It's important to see like Atlas software getting out and people start playing with. I have maybe two questions. One is a bit technical to understand a little bit the workflow. So the TopCP toolkit has its own YAML file which configures the TopCP toolkit, right? And then I guess there might be another YAML file which configures the whole ServiceX thing that takes FunkIDL. For example, if you have you presented various transformers, and I guess uproot transformer or FunkIDL transformer, these take their own configuration. But TopCP toolkit has its own. So how do you treat these various configuration layers? Is it two YAML files, or does this make sense?
I guess the question is, how do you, so each transformer has its own input, right? And the input is, I guess I'm a little confused on the question.
Yeah, I see Peter just replied. Maybe Kingion or Peter can take
Yeah,
this.
I can come in. Like if you go to like if you resume your sharing, like your shadow code for ServiceX request. Yeah, as shown here, like this. Yeah, this doesn't need to be, I mean, YAML. In principle, you can just use your Python function, or in Python you can submit ServiceX request, and the TopCP toolkit configuration YAML file can be passed like shown here, like query in the query. Yeah.
Right.
And also,
and this can be the only configuration file you will have, right? The TopCP toolkit configuration, that's all. You give some Python lines and you consider, this can be your only place where you define your analysis.
Yes.
Nice.
Pretty much, yeah.
And then another thing, can we plug another piece of software to run and do something on the output N-tuples of the TopCP toolkit? Can I do some histogramming and take back histograms or workspaces for statistics and stuff?
TopCP toolkit might be able to do that stuff. I'm actually not sure though. But yeah, once you have
I see. Peter replied. Okay.
Okay.
Okay. Good to know. Good to know also the scope of the project, guys. So
Mm.
yeah, that's good. Thank you. Thank you.
All right. Thank you, Alex, for your presentation, and thanks to the mentors for chiming in to help out. So appreciate it. Up next is Oleksandr.
Yeah, so today I'm going to present one of the, I would say, intermediate steps of my project, because I would not say that it's finished. The topic of my project was advanced ML techniques and dual readout systems for electroweak jet identification, particle flow enhancement, and future collider detectors. I'm from the University of Manchester, and my mentor, Christopher Tully. So let's start from the short review of my introduction talk. So basically, I'm working with dual readout systems in CEPC calorimeter, so that's segmented crystal electromagnetic precision calorimeter. And the aim point of my project is that's the determination of centroids and the enhancement of the resolution of our predictions. And it's so what this centroids basically is, it's a center of like points. It's the centers of gravity in our electromagnetic showers, and it's quite vital for reconstruction, especially for the determination of photon direction. What is hybrid dual readout systems? It's basically systems that it measures Cherenkov and scintillation light simultaneously for separation of hadronic electromagnetic components of the shower. So as I already said, my work was aimed to use machine learning techniques and build the model for determination of the z positions of the centroids and to increase the resolution of our determinations. So I also use data alongside with my projects. I use the data generator based on Jean-4 that was being also developed. So, and let's go to the machine learning architecture, and one of the most complex choices that I faced during my project. Previously, I mentioned that I intended to use CNN, which were quite promising because it can capture the spatial data, but without corresponding mapping. I will explain it a little bit later. We can choose another approach, like basic FNN, or like feed-forward network, or RNN, that's a recurrent neural network. But the main difference between them, that's a recurrent neural network, can capture the evolution of our data with time. Basically, it can capture how energy deposits through the certain layer, and it's more general, and it's like more versatile technique than FNN that can just treat features independently. Therefore, it was useful for me to compare them, the performance and the like generality of my model that will be discussed further. So, and there's the first results. So I started from the barrel and ADCAP crystal layers. Initially, we can see that the precision of RNN model and it's worse than FNN model, but at the same time, I would say that FNN model shows some kind of bias, especially it cannot, as I already said, it cannot capture the more how energy propagates in the layer. Therefore, it's more direct approach, and I would say less less. It just cannot capture more features and cannot capture how actually how data change with time. So therefore, the precision for NNN model achieved around 0.02 millimeters for 5 millimeter crystals. That's impressive, but I would say in a long term, the RNN can be more promising, especially if the model can be more improved. So yeah, and I would say overall the RNN can provide more robust solution than FNN. But next we can start seeing it more vividly, because in increasing the amount of data and starting working with timing layers, it was that so timing layers basically designed what's the difference between barrel and N-cup crystal layers and timing layers. The timing layers are designed for not only for defining the positions, but also for mainly designed for defining the timing of the interaction. And as we can see here, the FNN model breaks down almost completely, because it's already cannot predict so precise as we need, as the difference between the true value. The true value was predicted by the analytical approach, while the RNN capturing the evolution of our data can, for each event, can be more precise and can understand how and can actually predict the right results. So it just because of the lack of temporal dependencies and sequential interactions in FNN. So basically FNN was not developed for that, but at the same we can see here that FNN will not be able to it can be used only for spatial cases, but RNN not. So, and overall, why do we speak about timing layers and other layers differently? Why do we not use the data from all of them simultaneously at the same time? Firstly, I would say that that's because it can be a good simplification for the start, as capturing more, trying to feed our model more data can lead to overfitting, and also it's just hard to and overall model cannot just understand the one of the major problems that I will tell a little bit later, but so overall it's just a simplification. And the second one, alongside with my project, as I already said, the data generator was being developed, and I'm not sure for now, but when I got my results, the final release, I would not say final, just the release of the full simulation was not yet developed. So yeah, therefore I treated them differently, but at the same time, so it's good. So, and why I would say that, so basically the where did they stop? So I would say that project cannot be finished for now, because as we see here, it struggles with generalization. The aim purpose of my project was, as I already said, its determination of positions of centroids and the improvement of resolution, but it cannot be achieved without the main the main problem of the model is it cannot understand. It just don't know what detector is. It doesn't know how it works. It doesn't know what layers it has. So the next stage, it will be the improvement. It will be the teaching of the model what detector actually is. What the segmented Dual-Readout calorimeter, what's that? And only explaining it, we can reach the we can actually show our model how our data can be mapped, how actually energy propagates, so where is its sensorities positioned, are positioned. So, and that will be the next stage, that will be the next phase, and it will be quite complex, because I'm not sure that I'm gonna using Python in that stage. I guess I will switch it to C++ probably. So, and there I can tell that probably the RNN will be also, it can be mixed with CNN or completely changed to CNN, because with understanding what the model, what the detector is, the CNN model can be even more promising, because, as I already said, it works with spatial data, while RNN works with more sequences and evolution of data. So yeah, and that's one of the major goals, and I believe that I'm gonna work on this further. And that's my references. Thanks a lot.
Thank you, Alexander. And any questions or comments? Nice work. So, up next is Rimantas.
Okay, so my name is Rimantas, and I would like to present my project. So I titled this presentation, oh, maybe I should, yeah, hide this. Yeah, I titled this presentation Interface for Rapid Geometry Modeling and Exchange between CAD Tools and Simulation Platforms Dedicated for High-Energy Physics Experiments. So to put it simply, the goal of this project is to import the detector models made with CAD tools into Giant4 simulations. So the simulation toolkit that we are using is Giant4. CAD tools, I think you are familiar with. They're 3D modeling tools. So I'll just start off by explaining Giant a bit. So Giant4 is a simulation toolkit. It can be read as geometry and tracking. It's a toolkit designed for simulating the passage of particles through matter. So, for example, if we had a situation where we have two particles colliding, during the collision, secondary particles are created, and they fly out in different directions. So if we assume that these particles move towards a detector, they interact with the detector, they interact with the material of the detector. So when we have this interaction of particles with the material of the detector, we can simulate this process using Giant4. So the applications could be simulating any detector setup, because Giant allows us to freely define the shape of the detector, the geometry, and we can record physical quantities resulting from particle interactions with the detector. Giant is also great because it describes physics processes very accurately. It can include electromagnetic, strong, weak interactions, and it can also describe events in a wide energy range. So low energy events, high energy events. Giant4 is very flexible. So where is Giant used? Of course, it is used a lot in high energy physics. It can be used for simulating new detectors, for designing new detectors. We can design new detectors and test them out using Giant. Also, it is useful for generating detector data before we actually turn on the detector for the first time. This is useful because when we finally turn on the detector, we get a huge amount of data. So generating the data before actually turning on the detector, we can prepare for the data analysis. And when the detector is running, of course, Gent can be used to help make sense of the gathered data. Other than high energy physics, it can be used in space science for evaluating the effects of space radiation on satellites, for example. And it can also be used in medical physics. Now I would like to give an example of how a simple Giant program might be structured. First off, let's make it clear that Giant is not a full program which can run by itself. It is a toolkit which allows users to write their own program for simulating events. This makes Giant very flexible because it allows users to customize their programs for their own needs. And of course, it allows users to fully access the code and understand how it works. So a simple Giant program would be one that includes these parts. First, it includes the physics list. We define the physics process which will be simulated. For example, we can include electromagnetic and weak interactions in our simulation. Then we define the particle generator. So we define the number of particles, the type of particle, and then we define the detector geometry, which includes the shape of the detector, the material, the position, the rotation. And if we have a more complicated detector setup, then of course, for each part of the detector, we have to specify the position, the material, and so on. So this last part, the geometry part, is what my project is about. The other aspects I don't really work with. I work with the geometry aspect. One of the difficulties that can arise when making Giant simulations is the one of including complex detector setups. Giant allows the user to include complex detectors, but actually defining them in the simulation can be very challenging. For example, one of the ways the user can define detectors for Giant is to just write out the detector code by hand using C++. For simple detectors, this isn't a problem, but for complex setups, it is very time-consuming, as we have to define the shape position of each shape. And later, if we want to make adjustments, it can also be very difficult to do. So for complex setups, it is best to use 3D modeling tools to design the setup and then import it into the simulation. This process can also be tricky, so we are trying to make it as simple as possible. What we are doing is we're using a program called FreeCAD. It is a free software for creating 3D models. And we are trying to make the process of importing these FreeCAD models into Giant as fast and simple as possible. Now, what is nice about FreeCAD is that it's written in C++ and Python. So using the FreeCAD libraries in Python, we can open the FreeCAD model and automate some processes. So the first step of our process is that we take the FreeCAD file and using a Python script, we can easily split up the model into multiple STL files. For our test, we mainly use the model I'm showing right now. We got it to export successfully, and it produces 9 STL files. What's nice about this is that later when we import these shapes into the simulation, we can control the positioning and material of each shape individually. So it's nice to have these separate files. Now, figuring out how to export these shapes was quite interesting because the way FreeCAD stores the information about objects can be quite complex, especially for more detailed models. Each shape in the model can have many layers. Objects can be nested one inside of another many times, and we have to find only the relevant objects because there are also many objects which don't store information about the actual shapes. For example, in this diagram, if we want to export part 1, we have to get all the shapes which make up the parts. So we would have to get cylinder 1, cylinder 2. We would have to get the cube, the sphere. We would have to get the correct positions of the shapes, merge them together, and finally export this final shape to an STL file. So our script recursively goes through the objects, finds the information about the shapes, and merges the shapes. Once we have our STL files, we want to import them into our simulation. Since John doesn't allow us to directly import STL format files into simulations, we use a tool called CAD Mesh, which converts the STL shapes into a format which can be used in John simulations. It's a tool which is also written in C++, and it is easy to include it in a John program. The settings for each detector part are stored in a TOML configurations file. The file has a list of parts we want to include in the simulation, and it has the path of each STL file. We can also adjust the position, rotation, and material of each part. We can exclude some part if we want to. To make it simpler for the user, the settings are automatically generated by the Python script during the STL file exporting, so the user doesn't have to include the files manually. And the files are exported in a way which makes it so that setting the position to all zeros makes the detector appear in the simulation exactly as it does in the FreeCAD model. Now, just to give a quick overview of what we have done so far. So currently we can easily export FreeCAD models to STL format. We can export the detector into multiple STL files. We can import a single STL file into our simulation. During the last few weeks, we managed to make it so that we can also import multiple STL files. So currently we can actually import the whole detector geometry into our simulation. And we can change the position of each detector part by adjusting the TOML configuration file. Also, what's nice about the TOML file is that since we're defining the geometries inside the TOML file, we don't have to recompile the program each time. We can just change the settings in the file and run the program again, which makes it faster. Now, we still have a few weeks left for our project, so we want to make some improvements. We want to make a simple user interface for configuring the geometry, exporting and importing. Currently, when we export the FreeCAD model to STL, we have to include a list of parts that we want to export inside of the code. We have to define it inside of the code. So it would be nice to have the option to select which parts to export in the user interface. So overall, in the next few weeks, we will work on improving the user experience. And a quick summary. With this project, we aim to simplify the detector design process for Giant Force simulations. We aim to create tools which would allow to easily import and control detector parts designed using CAD tools. Thank you all.
Thank you, Rimantas. Any questions? Nice talk, thank you. Who's up next? Sorry. Sam, you're up next.
Hello, my name is Sam Kelson, and today I'll be presenting the development of experiment-specific data schemas for Coffea. So thank you for that's nice introduction. But I am Sam Kelson. I am a senior in the physics department at Brandeis University. My mentors were Lindsay Gray, Nick Smith, Matthew Feickart, and Jordan Stark. So a quick shout out to them. So what is Coffea? Coffea is the columnar object framework for effective analysis. And it is a library designed to integrate various essential components for conducting analysis at high energy physics experiments using the scientific Python ecosystem. So in Roots, our data frame, which is kind of like the analogous thing, kind of, when you analyze your data, you're going through each event in what's called an event loop. You go through each event, you do analysis on that one event, and then you do it for all the events in your loop. So you might be going through maybe 10,000 events per file. With a columnar approach, which is what Coffea uses, you do this in a column way. So you go through each column, you transform each column one column at a time. So instead of working with a single event at a time, you're working with a single parameter at a time per se. And this has some benefits as opposed to Roots, our data frame. It has the potential to be faster, and it has the potential for easier of use to because it's more familiar with NumPy's ecosystem for people who work with Python. Yeah, because that's what most people learn in undergrad. Another thing is Coffea is working to be integrated with other software called one specific software is Dask, which is a task scheduler. So pretty much what that means is you have a certain amount of computation resources. Dask will allow you to distribute your work to those resources very easily. So in my previous experiences, I've worked with Condor before, where Condor, you just say, I want this much computing resources, and it'll give you that much computing resources. But it's kind of hard to distribute the work to those resources. And as soon as a job's done with that resource, you lose that resource. With Dask, you keep that resource, and it's a lot more efficient as you can keep peddling out tasks to those resources without losing them. And so it makes work really efficient. And so by harnessing these modern distributed computing technologies, such as Dask, Coffea enables seamless scalability of HEP analysis from initial testing on, say, a laptop with maybe one file to a large computing cluster with a million files even without requiring modification of your code at all. And it's really about just working with Dask, which in my opinion is a lot nicer than working with Condor. Additionally, Coffea uses awkward arrays in the background. And so pretty much sometimes in computation, we sometimes separate the data structure with what it can do. So you might have, so an example is a Lorentz vector. It is technically just 4 numbers, but it has a lot more it can do than just those 4 numbers. It has certain properties. You can scale, you can do a dilation, whatever. So you can scale these. And so we want to keep, the goal in Coffea is to keep the data structure really closely related with what we call its behavior. And this is kind of an object-oriented design approach. So the goal of my project was the experiment-independent functionality for Coffea. And so what that means is that no matter what experiments we're using, could be Atlas, could be CMS, we should be able to have independent schemas, data schemas that fit these experiments. And so as Coffea continues to be adapted across a spectrum of AP experiments that employ diverse data formats, maintaining experiment-specific schemas that prioritize user-friendliness and performance become like an increasingly complex job. And so the primary object of this project is to address these challenges. And initially, well, pretty much consistently throughout the project, the focus was on Atlas's PHYSLITE data format, which is going to be the format for the next few runs of Atlas, hopefully. And so it promises easier of use too. And so Atlas is developing the schema currently, and so the goal with Coffea is to be the support schema. So what did I actually do this summer in terms of what was happening? So as PHYSLITE gets updated, there's certain bugs get introduced with our schema because we have to kind of parallelly work on, as Atlas works on this schema, we have to update our schema here at Coffea. And so that can be an increasingly hard task as we have a lot of hard-coded objects sometimes. And so one of the first things I had to do, and what I was doing through most of the summer, was beginning to learn how Coffea works, and then fixing a bunch of bugs that we had with our PHYSLITE data schema. And again, this is because PHYSLITE kind of grew faster than we were adapting to it. So the most important thing I did a lot of bug hunting. We found bugs in Coffea, we found bugs in Uproot, and most of those are fixed. Most of these bugs are resolved around something called element linking, where we have, say, an electron and the particle that's the track particle the electron came from. And so we want the electron to be able to link back to that track particle so analysis could know what that particle came from. And so it's important that these links work correctly. And previously that was always an issue, but now it's greatly improved and it's a lot more readily usable and won't throw errors at you. But what I'm currently working on is, and what I hope to continue working on, probably after grad school applications, but what I hope to continue working on is improved metadata reading for Coffea and Uproot in general. Something I'm really interested in is Root has a lot of C objects that Uproot can't really read, and it's important for able to, at least maybe not the most efficient way, but it's important for us to be able to read these objects because they contain a lot of useful data to us, such as metadata. And metadata can help us determine what objects we are linking to, especially in element links. One problem I had was when you're going to a new link, you usually don't know what object you're going to be linking to sometimes, unless you have it hard-coded earlier in the program. And so if we read the metadata before we actually load those element links, we can know what we're linking to before we actually open it. This is a lot more efficient because we don't have to open a new column because we know what it is a priori. So what this could do is, again, as I was mentioning, is we have a lot of hard-coded objects. So you can see on the left, we have these hash targets. We have this hash table that we have to convert from the hashes that is stored in the element links to what the actual object is. Now, this is hard-coded, so that means if a PHYSLITE is ever updated, these element links have to change too. These hash codes have to change too. And so in the future, what my hope is that you say you have 1,000 files, you assume all the metadata is the same for each file. You load one file, you read its metadata. The metadata contains the objects and their associated hashes, and therefore you have a hash table that you can work with. And therefore you know all objects you're linking to without loading the actual objects themselves. Yeah. So one thing I didn't get to in terms of performance testing was there were some issues with memory usage being weird, and I didn't fully explore what the computation times were for PHYSLITE schema with and without Dask. And this is something important to do because we want to make sure it should be approximately the same as with other schemas. So we want to make sure we're not falling behind. And it's something that I also needs to happen for our PHYSLITE schema in Coffee. Special thanks to my mentors, Lindsay Gray, Nick Smith, Mikey Feigenhardt, Jordan Stark, and Evangelos Gerlis for his tips with the PHYSLITE data schema. And are there any questions? Thank you for listening.
Thank you, Sam. Vangelis?
Hi, thank you, Sam, again. I think that's great work and really help us from the Atlas side. One question I have is a little bit on this metadata and the future work you kind of, as I understand, this is not done yet, and it's
it's just proposed.
Yeah, let me go back to understand a bit better. So indeed, at the moment, we have these numbers and we correspond to collections, and then you want to do this automatically in a way. So if I'm correct, with Coffee, before you do any dot compute, if you do nano events, whatever, open PHYSLITE file, there you do some metadata reading. And maybe this can be done at that point, just a single file, you open a single file, even a single event, and then you can do some metadata reading and then make these relationships, and then, this for good. Is it something like this you have in mind?
Yeah, that's what I had in mind. Currently, we have problems with elements. Like, again, I mentioned element linking. Currently, like, there's not really a way to know what the element you're linking to without this hash table. Because all that's stored in that development link, all that's stored in the root file is the unique identifier for that link, which is the hash I mentioned, and then the index in the event itself. And so you don't know what these are unless you load something first. So either you could directly load just a single event and do it that way, or you could read the metadata that's actually stored in the file. I guess either way works. Yes.
Yeah. So we'll discuss maybe tomorrow as well. I'll try to figure out how this hash to collection correspondence is
that's what
planned to be evolved.
I know it's based on
this might stay the same forever. So
yeah,
I'm not sure about that. I need to ask some people. Are we gonna keep this forever? Is this something that might change at some point? But let's follow this up tomorrow. Thanks again for this awesome
sounds
work.
good. Yeah, I'll see you tomorrow. Any other questions?
All right. Thank you, Sam. Next up is Volodymyr. Okay.
I've prepared a quick showcase on my summer fellowship progress. Table of context. I want to recall my goals from the proposal. You can see that the goals were to modernize some scripts, models, and spoiler, they are all modernized already. Assigner was modernized by other students. But Auto ACDC and Actor, they were migrated by me. And also, I decided to bring up GitLab activity because it's the most obvious way to show my activity rate. Let's move on the progress flow. First of all, I had to get familiar with the old repository, but beforehand, I had to access the inner network of the CERN. It was the new experience for me. I've got some certificates, and also it was very interesting for me. That after all of the accesses were granted, I began to explore the old repository, keep track of the functions, methods, classes, and started thinking on the new implementation, and also P&R team. That's the team which is responsible for the resubmitting of the workflows, and the workflows are the distributed parts of the great calculations which are processing the CMS detector data. So the P&R team had some repo with the new classes, and I began to work. During the 2 months, I've successfully migrated auto-ECDC script into the new repo, and the runner script into the new repo. As you can see, the screenshot. Actually, I cannot show you the result of the work because everything that those scripts do, it's on the backend, because the main target or the main purpose of those scripts is resubmission of the jobs with the new parameters. But suddenly, my mentor suggested me to participate in the development of their front-end page, P&R's dashboard. They are using this website to resubmit workflows. So I agreed. Their front-end page uses React framework. I have not been familiar with the React at that moment, but I decided to catch up quickly. I've learned some basics and quickly begin to develop a UI which is used to create one JSON string, which usually P&R teams members type in manually, form manually. So I've created a convenient UI for them to change some parameters for workflow, or each workflow has tasks they can customize, and it builds a JSON. Also, you can click on the chip and edit, so it's quite convenient. And also, it is part of the UI. This smart site resolver shows the sites where a job failed and automatically excludes those ones, but a user can manually undo exclusion. So let's move on. Skills which I gained during the summer fellowship. Actually, I was a bit familiar with GitLab before the summer fellowship, but during the fellowship, I've discovered many more features in the GitLab. Also, I've discovered what is unit tests and how to write them. I've created personally 2 unit tests. Also, I was working with Docker because in both cases, with front-end page and the backend scripts, they are using Docker. And the last thing is not actually last thing. I've learned some React basics with framework, and also not very expected, but I've learned one new unfamiliar before for me Visual IDE, actually Visual Studio Code, because my mentor advised me to use Visual Studio Code, and it was really a very enjoyable experience. Thank you for your attention, and I'm ready to hear your questions.
Thank you, Volodymyr. Any questions for Volodymyr? All right. Thanks, everybody. That's it for today. Thank you to all the fellows for their talks. Thank you to the mentors for guiding the fellows. We have another round coming up on Wednesday. And that's it for today. So thank you all.